Am I recording? Yes, I am. Alright, atomic concepts. We need to know, I'm going to move this to the side. We need to know the history of the atom. Okay. Started with Democritus and Aristotle. Way back. And they coined the term atomos, which means small indivisible, right? Small particles. Spell it right, Kaufman. What happened here? And then nothing really happened for a really long time until John Dalton came along. Okay. John Dalton said that the atom was composed of indivisible spheres. Indivisible spheres. And we call this the billiard ball model. Billiard ball model. Okay, I'll draw a timeline when we get done with it. Okay. After Dalton was J.J. Thomson. He discovered the electron using something called a cathode ray tube. And a cathode ray tube had these negative particles shooting out, and he was able to manipulate them. He found out they were negative because they were attracted to the positive magnet and repelled by a negative magnet. So he discovered the electron. Then came Ernest Rutherford. Oh, sorry. I should go back. I didn't say his model. Thomson had the plum pudding model. All right. The plum pudding model looked like this, where you had negatively charged particles embedded in a positively charged pudding. Okay, so all this white space was positive, and then he said there's something negative in there, I just don't know really what it is. And Ernest Rutherford, this one's the one you're going to put a star next to, did the gold foil experiment. And he had the nuclear model. Okay, so this is what he did. He took a box, and in the box he had a lump of radioactive material. That lump of radioactive material gave out alpha particles. These are alpha particles. Alpha particles are nothing more than a helium, a 4/2 helium. That's what an alpha particle is. And he shot it at a piece of gold foil, which my gold foil is going to be purple. Okay. And he noticed that most of the time, there was a shield back here, most of the time the alpha particles went straight through and made a spark right here. But every once in a while, an alpha particle bounced back and seemed to come back in the same direction from which it was shot. Okay, and it would hit over here somewhere if this thing went around like that, this shield that he had around it, there would be another spark over here. Okay, so most of the time it went straight through, but every once in a while, oh, I should have drawn this. I'm sorry. This shouldn't have gone there. It should go here. Alpha particles. They never went straight through. They just bounced back from the paper. So most of the time they went through, sometimes they bounced back. And he said, hey, why does it bounce back? Well, it must have bounced back because it hit something. What did it hit? The nucleus of the atom. That's what it hit. Okay? So Ernest Rutherford had two main things that he contributed to the structure of the atom. The atom is mostly empty space, and that it had a hard, dense, positively charged nucleus. This is on every Regents, every single one. Okay. So when it went straight through, that proved that it was mostly empty space. When it bounced back, it proved that it had a hard, dense, positively charged nucleus. And his model was called the nuclear model. It looked like this, with negative all out here. Those are negatives. These are negative. And this right here, I'll make it red so it stands out, is positive nucleus. And what happened was, every time one of these alpha particles got close, it would shoot it back in the opposite direction. Then, after Rutherford, came Niels Bohr. Niels Bohr had the planetary model. And what that said is that electrons, which are the negative particles now, are traveling around the nucleus like planets around the sun. So there's the nucleus in the middle. And then he said, all right, well, they're not kind of just all scattered around. There are these rings right here. That one's not a good arrow. Okay. And these rings are these energy levels, where the one that's closest to the nucleus, which is n equals 1, and this would be n equals 2, and then the third one, this is 3, this is n equals 2. Okay, 1 is the closest to the nucleus, 2 is the next one, 3 is the one out here, where they have different amounts of energies, and the electrons have to be on one of those energy levels. The electrons closest to the nucleus have the lowest energy levels. So n equals 1 is lower energy than n equals 3. This is on almost every Regents. The further you get away from the nucleus, the more energy you have. Okay. Bohr also told us, I'm going to switch colors just to make it a little bit more interesting here, the number of electrons on each energy level. N equals 1 can hold 2, a maximum of 2 electrons. N equals 2 can hold 8. N equals 3 can hold 18. N equals 4 can hold 32. You don't need to go higher than that. That's how many electrons can fit on each energy level. And there's a nice little formula, 2n squared, where n is the energy level, and it tells you the number of electrons on that level. Okay, so Bohr had the planetary model. Then after Bohr, we have the modern model. In the modern model, you have a nucleus, but the electrons are traveling in orbitals around the nucleus. Not orbits. They're not traveling like planets around the sun, staying on the same path. They could be anywhere in a three-dimensional shape. So in the modern model, sometimes this is called the wave mechanical model. Both are the same thing. Remember, that's your keyword, orbitals. Okay? Okay. Any questions on that? Okay, atomic structure. You've got a nucleus. Inside the nucleus, you have protons and you have neutrons. Outside of the nucleus, I'm going to make them red. I'm drawing them like Bohr diagrams because it's just easier for me than in a modern model. You have these rings, these energy levels that have electrons on them. Those are your electrons. And the electrons are negatively charged. Protons are positively charged. And neutrons have no charge. I'm going to draw a chart for you so you have them all in one place, okay? Protons, neutrons, and electrons make up the atom. Where the protons and neutrons are in the nucleus, electrons are on the outside. All right, let's draw the chart. Protons, neutrons, electrons. Mass, charge, location. Okay. Protons have a mass of 1 atomic mass unit. An atomic mass unit is 1/12 the mass of a carbon-12 atom. Okay, that defines an atomic mass unit, AMU. Neutrons are also 1 atomic mass unit. So these guys, protons and neutrons, weigh almost the same amount. They're a little bit different, but we're going to round them to 1. Electrons weigh 0 atomic mass units, or 1/1836 the mass of a proton. In other words, if you took a proton and you divided it into 2,000 parts, or almost 2,000 parts, one of those would be an electron. It's really, 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 really small. It's so small that we say that it has no mass. Okay? The charge on a proton is +1. The neutron has no charge, and an electron has a charge of -1. Protons and neutrons are in the nucleus, sometimes referred to as nucleons. And an electron is in an orbital. An orbital is simply just a three-dimensional region of space where you're going to find an electron. How's everybody doing out there, okay? Is this helping or hurting? It's a lot. Okay. Okay, so know this chart. Protons, neutrons, electrons, mass, charge, location. So the protons, one more time, is 1 atomic mass unit, positive 1, it's in the nucleus. The neutrons weigh 1, they have no charge, and they're in the nucleus. And an electron weighs nothing, it has a negative charge, and it's in the orbital. Okay, any questions? All right, I want you to look at your reference table on the periodic table. Let's talk about electron configuration. Okay, when you look at your reference table, in the bottom left corner, there is a string of numbers, and it's labeled electron configuration. Do you see that there? The electron configuration tells you where the electrons are living in what we call a ground state. So when carbon atoms are in the lowest possible energy, the electrons, 2 of them are in the first ring, so here's the nucleus. Okay, and it's got 6 protons, 6 positive P's. And the electrons are out here. In the first ring and in the second ring, you have electrons. I'm sorry that they're not round. Okay? In the first ring, you're going to have 2 electrons. 1, 2. In the second ring, you're going to have 4 electrons. Like that. Okay? That's what these numbers mean. When they're in ground state, they're in the lowest possible positions. You can excite those electrons. You can get them to go to higher energy levels by exciting them. That means hold a candle to their butt and watch them jump, right? So if I took a candle and put it to Will's butt, what is he going to do? It's going to jump, right? So if I put a candle to this electron right here might say, hey, I'm going up here to get away from the flame. Now it is an excited state electron configuration. So instead of being 2-4, I have 1-5. Okay, 1-5 is excited because this first energy level, which can hold a maximum of 2 electrons, because that's what Bohr told us. Bohr told us the first energy level can hold 2 electrons. Because of that, whoops, let's get this electron back where he belongs. Okay. That electron energy level is full. But as soon as I light it on fire, it jumps to a higher energy level. Now it's not full. This one's not full anymore, so it is excited state electron configuration. Let's look at how you can tell if something is ground state or excited state by just looking at the electron configuration. If I give you 2-8-2, and I say, is that a ground or excited state electron configuration, what would you do? Okay, you would add them all up. That would give you 12 electrons total. If you have 12 electrons, the number of protons is equal to the number of electrons in a neutral atom. So if I have 12 electrons, then I know I have 12 protons. What element has 12 protons? Magnesium. Okay, so look at magnesium's box. Does this electron configuration match what's in magnesium's box? Yes. Magnesium's ground state electron configuration is 2-8-2. It only has one ground state electron configuration. and it's given to you. So because it matches it, it's ground state electron configuration. Got it? All right. What about 273? That's still going to have 12 electrons. But does it match magnesium? Well, it adds up to 12, so it's got to be magnesium. Does that match magnesium's electron configuration? Nope. So this is excited state. Magnesium. This one was ground state. Magnesium. See the difference? There's only one ground state, and it's given to you. There are multiple excited states. 2, 8, 4. Ground state. What element is it? Silicon. That's ground state silicon. Give me an excited state silicon electron configuration. 275. Okay? Be very careful. When you are moving from a ground to an excited state, the easiest way to do it is to take one off the last ring and just pop it up to its own new ring. That way you don't overfill anything. This third energy level can only hold a maximum of 8 electrons when it's a valence shell. Right now it's a valence shell. So just be careful with that. So I would do 2-8-3-1, and then there's no chance I would overfill this because I made a new one and I put 1 electron in it. So just be careful with those. Okay? For example, let's do 2-8-8. What element is that? It's argon. If I went with Will's way, it would be 2-7-9. That's wrong. Because this outside ring can't have more than 8. Okay? That's why I wanted to show that to you. I want to make sure you don't overfill anything. I would do 2-8-7-1, and now I have excited state argon. Okay? Questions on that? Okay. Valence electrons are the outermost electrons. They are the electrons in the very last ring. So if again I have magnesium 2-8-2, it has 2 valence electrons. And the valence electrons give us the chemical properties of that element. So all of the elements that have 2 valence electrons share similar chemical properties, and they're going to be in the column based on that. So in this case, because it has 2 valence electrons, it's going to be in column number 2, which is group 2 on your periodic table, also known as the alkali earth metals. You okay, Michael? Mm-hmm. All right. Emily, you good? Okay. Let's see, what's next? I talked about that. I talked about that. I talked about that. I talked about excited state. I talked about valence electrons. We should draw some Lewis dot diagrams of electrons, and then we'll go into isotopes. Okay. Lewis dot diagrams. Are based on valence electrons in the atom. So if I have carbon, what's the electron configuration of carbon? 2-4. That outermost ring is the valence shell. That means it has 4 valence electrons. If it has 4 valence electrons and I draw the Lewis dot diagram for carbon, then it's going to get 4 dots around it. When you draw the dots, I want you to draw them in this order: 12 o'clock, 3 o'clock, 6 o'clock, 9 o'clock. If there were 5, I'd go back to 12 o'clock, then 3 o'clock, then 6 o'clock, then 9 o'clock, until I go around the clock once and around the clock twice, right? 12 o'clock, 3 o'clock, 6 o'clock, 9 o'clock. 12 o'clock, 3 o'clock, 6 o'clock, 9 o'clock. Example, neon. How many valence electrons does neon have? 8, 2-8. So 8 valence electrons, I would take neon. I'd go 12, 3, 6, 9, 12, 3, 6, 9. Neon. Oxygen. How many dots is it going to get? 6. 12, 3, 6, 9, 12, 3. Aluminum. How many valence electrons? 3. 1, 2, 3. All right, we good with valence electrons and drawing Lewis dot diagrams of them? Okay. All right, in this unit on this page, we have something that gives us the I words. There's 3 I words. 3 I words. Ion, isotope, and isomer. Okay, we're going to skip isomer for now. Even though my people, Olivia, Nora, you know what an isomer is, I don't think you guys got to it yet. Okay? Because Mr. McGregor's just starting organic with you, and isomer is in the organic chapter. So we'll get to that later. But ion and isotope. Let's talk about what an ion is and what an isotope is. Ion, you're changing the number of electrons. When you gain an electron, you become negative. When you lose an electron, you become positive. A negative ion is called an anion. A negative ion is called a cation. What's that? Oh, I'm sorry. Positive ion is a cation. Negative ion is an anion. Okay? So ions change the number of electrons. You're not changing proton number. You're not changing neutron number. You're only changing the electron number. Isotopes, you change the number of neutrons. So when you change the number of neutrons, you're changing the mass. Carbon-12 and carbon-14 are examples of isotopes. They both have 6 protons, but they have different numbers of neutrons. This guy is going to have 6 neutrons. This guy is going to have 8 neutrons. Let me just write on another page so I have more room. You okay, Michael?
Yeah.
Okay. Just yell if I have to go back. All right. This number down here is the atomic number. It's also the number of protons. It's also the nuclear charge. This number up here is the mass number, if it's a whole number. It's the average isotopic mass if it's a decimal. Okay, it's the number of protons and the number of neutrons together. So when we add protons and neutrons, protons plus neutrons, we're going to get this number 12. Down here, we just have protons. So if I want to know how many neutrons I have, I'm going to take the top number and I'm going to subtract the bottom number. Mass minus atomic number gives you number of neutrons. Atomic mass minus atomic number equals neutrons. Top minus bottom. Bigger minus smaller is going to give you neutrons. Oh, I didn't say this, but it's on here. So, when you gain an electron and become an anion, your radius becomes bigger. And when you lose an electron and become a cation, your radius gets smaller. It has nothing to do with the actual electrons, but it has to do with the fact that if you lose an electron, you lose a ring. If you gain an electron, now we've got two negatives next to each other. They're going to push apart from one another and become slightly larger. Electronegativity. Electronegativity is a measure of how strong an element is. It's based on a scale from 0 to 4. 4 is the strongest. 0.6 is the weakest. Okay. Who has an electronegativity of 4? Fluorine. He's the bully of the whole periodic table. Who's the weakest? Francium. Okay. Look where they are on the periodic table. Fluorine is up here, strongest. Francium's down here, weakest. Okay. You don't have to guess on that, because on table S, let me plug my iPad back in, because there we go. Right here, they give you your electronegativities. So if you look at fluorine, it's a 4. If you look at francium, he's down here somewhere.
87.
Thank you, 87. He's 0.7. Okay? He's weak. Fluorine is strong. So that means if fluorine and francium meet in a cold, dark alley, who's winning the fight, Olivia? Fluorine. And they're fighting over electrons. So fluorine, let's not do fluorine and francium. Let's do fluorine, who has 7 valence electrons. Remember where we get valence electrons from, right there. And sodium, which has 1 valence electron. If these guys are fighting, this electron is going to go over to fluorine, because fluorine is stronger than sodium, so fluorine wins. Okay? And when that happens, sodium becomes a positive ion because he lost an electron. Fluorine becomes a negative ion. I just made them as X's. I don't know why. Don't ask. Because he gained an electron. Now I've got a positive and a negative, and they made a bond. What type of bond did they make? An ionic bond. This is a sodium ion. This is a fluorine ion. Together they make an ionic bond. Ionic bonds, which I'm assuming is going to be next week, are formed when a metal and a nonmetal transfer electrons. So the metal loses, sodium's the metal, fluorine gains. So the electrons go from metal to the nonmetal. Alright, did I hit most things in this unit? Let's see. I think I did most of it. Alright. Let's see what we got here. Experiments performed to reveal the structure of atoms led scientists to conclude that the atoms what do you think? 4. Mainly unoccupied. Mostly empty space. That's Rutherford. Mostly empty space, hard, dense, positively charged nucleus. The modern model, that's the model that we believe today. Soon as you see modern model, they're going to ask about the electrons, and sure enough, they do have the atoms show that electrons are where? In orbitals. Not in like planets around the sun, they're in orbitals. 3-dimensional regions of space. 3-dimensional region of space. An experiment in which alpha particles, soon as you see alpha particles, whose experiment is it? Rutherford's gold foil experiment. What did he say? He said mostly empty space, mostly empty space, and hard, dense, positively charged nucleus. All right, let's find it. Small, dense, positively charged nucleus. All right. What's the atomic number that has 6 protons and 8 neutrons? What is it? Nope. Atomic number. What's the atomic number equal to? Atomic number is the same as protons. So it's 6. If they had asked for the mass number, then it would be what? 14. Mass is protons plus neutrons. Atomic number is just protons. An atom of fluorine has a mass of 19 atomic mass units. The total number of protons and neutrons in its nucleus is, so it's telling us the mass, and it's telling us that it weighs 19 AMU. So, fluorine with 19 atomic mass units, how many protons? The total number of protons and neutrons in its nucleus is what? 19. If they had asked us how many protons it has, where would you find that? 19 minus, no, protons. Just 9. If they asked you for how many neutrons, then it would be 19 minus 9. All right, what is the total number of protons in a nucleus of carbon-14? Six. My sister-in-law just said I made it home. So that's good news. Okay. What is the nuclear charge of an iron atom? If you see the word atom, what's the charge on an atom? Always neutral. Atoms, by definition, have no charge. Okay? But they asked us for the nuclear charge. The nuclear charge is the charge of just the nucleus. What's the charge? What's the only thing in the nucleus that has a charge? Protons. So they're asking for the number of protons. What is it, 26? That's what I would pick. All right, which of these elements has an atom with the most stable outer electron configuration? That means it's going to have a full valence shell. Which one is it? Neon. full valence shell. That means the outside shell is full, and it's going to be one of these noble gases over here, including helium. Don't forget about him up there, even though he's cut off up here. Full valence shell. How many electrons are in the outermost principal energy level, that's the valence shell, of a carbon atom in ground state? Olivia, how many? You got this, kid. How many electrons are in the outermost energy level of carbon? Say it loud like you mean it. I'm going to go with you said 4, even though you didn't say it loud. All right. What's the electron configuration for a sodium ion? Okay. Sodium atom is going to be 2, 8, 1. The atom is neutral. 2, 8, 1. If it's an ion, it's going to lose this 1 electron on the outside valence shell. So it's going to become 2, 8. They want to know the charge of it, or they want to know the electron configuration? Electron configuration, 2, 8. All right, what's the electron configuration of a sulfur atom in the ground state? What? Sulfur? Yep, 286. Just right off the periodic table. The nucleus of which atom contains 48 neutrons? How do you find neutrons? Neutrons equals mass minus atomic number. All right, let's do it. 32 minus 16 is 16. That's not it. 48 minus 22 is 26. That's not it. 85 minus 17. Oh, could that be it?
37, I think.
What's that?
37, not 17 now.
Oh, you're right, yeah.
It's hard to say.
85 minus 37. I did the math right, but I was looking at the wrong one. Let's zoom in, because it's easier to see. Okay. 85 minus 37 is 48. So this looks like it's going to be my answer. And 112 minus 48, that's 4. That's 0. That's 10. That's 64. Okay? So 48 is what I'm looking for. 48 neutrons. Always remember, it's the top minus the bottom gives you the neutrons. The number of neutrons in the nucleus of an atom can be determined by, look, I just wrote it up here. Mass minus atomic number. Mass number from the atomic number. No. Subtracting the atomic number from the mass number. I like that one. Atomic number from the mass number, not the mass from the atomic number. Okay, 14. When an atom loses an electron, an atom becomes an ion. When you lose an electron, you become positively charged. And you become a cation. I don't think they ask us about that. And so positively charged can't be this one, can't be this one. Does it gain a small amount of mass or lose a small amount of mass? It's going to lose a small amount of mass because you lost an electron. It's a really small amount of mass. All right, in which pair of elements do nuclei of the atoms contain the same number of neutrons? All right, let's do them. 7 minus 3, that's 4. 9 minus 4 is 5, so that's not the same. 14 minus 7 is 7. 16 minus 8 is 8, so that's not the same. So neither one of these is my answer. 23 minus 11, so that's going to be 12. 24 minus 12 is going to be 12. Oh, looks like that's going to be my answer. 32 minus 16 is 16. 35 minus 17, 8 to 18. So that's not the same, so it's not this one. You guys okay over there? The characteristic spectral lines of the elements are caused when electrons in an excited atom move from, we didn't go over this. Okay, and this is always on the Regents. When do you get those beautiful spectral lines? When the electrons do what? They release energy, and where are they going? From high to low. Always remember, you see the pretty colors of the fireworks on the 4th of July when the firework is going from high in the sky back down to earth. You see the colors when they go from high to low. Okay? So they go from high to low energy, and they're going to release that energy in the form of light. When a lithium atom forms a lithium ion, the lithium atom does what? So it became positive. That means you had to lose an electron. What is the total number of electrons in the valence shell of an aluminum atom in ground state? How many? I like 3. 3 is a good number. It's a lucky number. Okay? The valence shell of aluminum is the last one. So it's asking how many electrons are in the valence shell? 3. An electron in an atom moves from the ground to the excited when the energy of the electron does what? When the firework goes from the ground up to the sky. Did you have to put energy in, or did you take energy out? When you got it to go all the way up, you put energy in, okay? So from the ground to the excited, when the energy of the electron increases. In order to get the firework to go up, you need to put energy in. That's why you put a little match to it and get it to go up into the sky. When do you see the colors? When it's coming back down and the energy is falling back out of the firework. All right, during a flame test, ions of a specific metal are heated in the flame of a gas burner. The characteristic color of light is emitted by these ions in the flame when the electrons do what? When do we see the light of the firework? When they are coming back down. Good. So when they're coming back down, they're moving to higher energy levels? No, I don't like that answer. They're returning to lower? Yes. Move to higher energy? I don't like that answer. So now we're down to 2 and 4. Are they giving off the energy, or are they gaining the energy when you see the light? Giving it off. Emit means to give off. What's the total number of electrons in a copper plus 1 ion? Okay. Usually a copper, where the heck's copper? He's around here somewhere. There he is. Okay. Usually copper has 29 electrons. But if it becomes a plus 1 ion, that means it lost an electron. So instead of having 29, it's going to have 28. If you become a negative ion, you gain electrons. If you become a positive ion, you give off electrons. All right. This is a popular question here. Identify 2 gases in the unknown mixture. Look at the unknown mixture and match them up. Here and here, right? So these lines match up with gas A. So we know gas A is in the mixture. And this line and these 2 lines match up here. So we know gas D is in the mixture. In order for the gas to be in the mixture, all of the lines need to show up in that mixture. Even though these 2 lines look like they might match up here, this one definitely doesn't have a line here. See it? It's not perfectly matched up, but I'm just giving you an example. Make sure that all the lines match. So we're going to go with A and D. Explain the production of the emission spectrum in terms of energy states of an electron. What are you going to say? When do you get to see the pretty light? The emission spectrum. This is the pretty light. I know you can talk louder than that. Perfect. So, state in terms of energy states. So, when electrons fall from high energy to lower energy, they give off the energy in the form of light. Good? Okay. Got some more Regents questions here. Alright, we'll be able to blast through these pages pretty quick. Which subatomic particles are located in the nucleus of a neon atom? Protons and neutrons are in the nucleus. What's the total mass of protons in an atom of gold 198? Gold. Gold has a symbol of Au. How many protons does it have? Total mass of the protons in an atom of gold 198. Only the protons. Did you find gold? It's right here. How many protons does it have?
I'm fine. Can you show it again? I'm sorry.
Yeah, sure.
How many protons?
Yep, protons only.
6?
Nope.
Oh, it's in the bottom?
Yep. This number right here is the number of protons. 79 protons in gold, okay? 197 is the mass. That's the protons and the neutrons. This is the protons. So it's going to have 79 atomic mass units. Okay? In a calcium atom in the ground state, the electrons that possess the least amount of energy are located in... We have the least amount of energy. Are we going to be close to the nucleus or far away from it?
Far.
Try again. Close. So here's the nucleus. The electrons that are closest have the lowest energy. The further away you get, the more energy you have. So I'm going to go with first electron shell. Alright, which group of atomic models is listed in order from the earliest to the most recent? So we had Dalton was first, then Thomson, then Rutherford, then Bohr. So we got, who came first? Dalton. What did he say? What was his model look like? Say it again? Yes, which is a hard sphere, right? Billiard balls are hard spheres. So it looks like 1 and 2 are still in the running. The electron shell is probably not the first one. Alright, so we got hard sphere. Then we have wave mechanical model or electron shell model. Which one came next? The wave mechanical model is the modern model. It's the model that we have today. Okay, so the electron shell model, that's Bohr. He's the one who said they were like this. And the wave mechanical model is the one that looks like that, where they're in three-dimensional regions of space. Okay? Alright, which isotope notation represents atoms of carbon-14? Carbon. What's its atomic number? 6. And this 14 is the mass number, so it looks like choice 4 is carbon-14. Which isotopic notations identifies a metalloid that is matched with the corresponding number of protons in each of its atoms? All right, first off, we need to find a metalloid. We didn't talk about metalloids yet. That's Unit 3, periodic table. Metalloids are on the staircase. They are B, Si, As, Te, At, Ge, and Sb. So these guys and these two in the middle here. Not aluminum, not polonium. So these guys. So let's find one of those. Magnesium is not one of those because that's all the way over here. So that's not it. So magnesium's out. Silicon is on the staircase, so that's got potential. Astatine, As, is... he's on the staircase, so he's got potential. And then bromine is over here. He's not on the staircase, so he's out. All right. We got silicon with 14 protons and astatine with 75 protons. Here's silicon. How many protons does silicon have? 14. And astatine has 33. So it looks like it's going to be number 2, silicon with 14 protons. 7. According to the wave mechanical model, that's the modern model. As soon as you see the modern model, I didn't even finish reading it, I'm thinking orbitals. Because it looks like this, right? According to the wave mechanical model of the atom, electrons in an atom travel in defined circles. Nope, that's the Bohr model. Are most likely found in an excited state? No. The only way to get to excited state is to light them on fire and make them jump up. Have a positive charge? No. Are located in bing, 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 orbitals. Anytime you see modern model, what are you going to pick, Olivia? Orbitals. Good job. All right. What's the total charge of a nucleus of a carbon atom? Hey, we just had this question already, didn't we? Nucleus of a carbon. The nucleus has protons and neutrons in it, and only protons have a charge. So therefore, the charge of a nucleus has to be positive whatever number of protons that carbon atom is going to have. How many protons does a carbon atom have? 6. Good job. A sample composed of only atoms having the same atomic number is classified as same atomic number. They're all the same element. Which two particles each have approximately equal to 1 atomic mass unit?
That was the table you gave us?
Yes, that's the table. Good job. So, which ones have approximately 1 atomic mass unit for their mass? Protons and neutrons. Trying to get back to my table here. Come on, you can do it. I really do need to invest in a new iPad. I just don't want to spend the money on it. I'm so terrible. I need a new phone. I need a new iPad. I need new AirPods. I just can't part with them.
Over time, AirPods just
Look,
got
it
more
won't
quiet.
even turn on. What about your AirPods?
They got more quiet over time.
Mine are going. Come on already. All right, I got to something. It kicked me out again. All right, let's go back to the chart. Find it. Ah, there it is. Okay. Mass. 1 atomic mass unit. Neutrons 1 1 atomic mass unit. Okay? So that's this question right here. Which two particles have a mass approximately equal to 1 atomic mass unit? Protons and neutrons. All right, which electron configuration could represent a strontium atom in excited state? Strontium is right here. We know it has 38 electrons in it, right? And this is the ground state, 2, 8, 18, 8, 2. 2, 8, 18, 8, 2. Okay. This better add up to 38. Okay. So you can do this. 18 plus 10. 18 plus 10 is 28. Plus 10 more is 38. So that adds up. Okay. We want an excited state, which means we also have to add up to 38, but we cannot have exactly the same that's there. 2, 8 is 10, plus 18 is 28, plus 9 is not going to give me 38. So this one's out. 2, 8 is 10, plus 18 is 28, plus 10 more is 38. This one's got potential. 2, 8, 18, plus 9, nope. 2, 8, 18, plus 10, this one has potential. Okay, so now they both add up to 38. Which one's the excited one and which one's the ground one, and why? Ground state is given to you here. 2, 8, 18, 8, 2. 2, 8, 18, 8, 2. 2, 8, 18, 8, 2. What's this one? Ground. They want excited. So it has to be this smiley face over here. Alright, 12. What is the total number of neutrons in an atom of iron 57? How do you find neutrons?
Subtraction.
Subtraction. 57 minus 26, as long as that's really a 57. I'm going to go with it is. So let's go 1 and 3, 31. 57, 5 minus 2 is 3, 7 minus 6 is 1. Yay. Okay, 13. What's the total number of electrons in a magnesium plus 2 ion? Well, when we look at magnesium has an electron configuration of 282. That's when it's neutral, 0 charge. If I become a plus 2, that means I lost these 2 electrons. If I lose 2 electrons, I don't have 12 anymore. I have 10. 10 electrons. 14. What was concluded about the structure of the atom as the result of the gold foil experiment? Positively charged nucleus, small, dense, positively charged nucleus, mostly empty space. That question is on every single Regents. 15. An atom is neutral because the number of protons equals the number of electrons. 16. How do the energy and the most probable location of an electron in the third shell compare to the energy and the most probable location of an electron in the first shell? Who has more energy, the third shell or the first shell? Third shell. The third shell, an electron has more energy and is closer to the nucleus? No. Good job. In the third shell, an electron has more energy? Yes. Is farther away from the nucleus. I like that one. Let's give that one a smiley face. In the third shell, an electron has less energy? No. In a third shell, the electron has less energy. So I'm going with 2. What is the net charge of an ion that has 9 protons, 11 neutrons, and 10 electrons? Net means overall. So if it has 9 positives and it has 11 zeros and 10 negatives, what is its overall charge? Do we care about the neutrons? No. 9 positives and 10 negatives. So what is its overall charge going to be?
-1.
-1. I love it. All right. Which value of the element is calculated using both the mass and the relative abundance of each naturally occurring isotopes of this element? If we want to use the percent abundance and the naturally occurring isotopes, you are looking at the atomic mass. 1 × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10 next week when we meet on Monday, remind me. I'm going to start with writing the average atomic mass and how to do it, because it is on every single Regents. What I would do is I would make a card and I'd be like, I know this is on the Regents, let me just find it. It's free points. It's there. I'm telling you it's there. It's on every Regents. And then, which two notations represent different isotopes of the same element? Same element, they have to have the same bottom numbers because they have to be the same element, same number of protons, but they are isotopes, which means they're going to have different masses. And if they have different masses, the top numbers are going to be different. So, this is a 6 and this is a 9. That looks like it's going to be my answer, because 4 and 4, same atomic number, different mass numbers. These are exactly the same. They are not isotopes of each other. These guys are exactly the same, except for they put different letters here. The letter is determined by whatever this number is. So if this number is 15, it's P. This number is 16, that's S. So these are totally different elements. And this is 7 and 6. 7 is nitrogen, 6 is carbon, but they have the same mass number. So these are not the same elements. Okay? Any questions? Please, before we meet again, try to do the rest of this page, front and back, and then next Monday, I will go over that with you, okay?